Hi, here's an exercise I particularly like because it has to do with the normal curve, and it's a hands-on activity that lets students explore the probability of something occurring where they can do it one way using the normal distribution table, but another way using Minitab because Minitab shows really nicely areas to the left or right of certain points on the normal density curve. So without ado, let me get to the problem. So we imagine that we're training students, let's say for flight school, and we're going to give them like a hand-eye coordination test. And the better they do, we're going to say you're more likely to end up going to our flight school. So this is just a free program I found online. It's called the Red Block Flight Simulator. That's what we call it anyway. And let me take you there. Here it comes. And so what you are in this game, you're the little red block and you're trying to stay away from getting hit by the blue blocks. They're going to come at you. You can't go out of bounds. You have to stay in the white region. And the object is to stay away from the blue blocks as long as possible. So the better you are at staying away and not going out of bounds, then you would have a higher score, and we would say you're more likely to join our flight team. So let me just give you an example of it. I'm certainly not great. So I'm the red block, and I move it with my mouse, and I'm just trying to stay away from the blue blocks. And eventually there are some patterns, and I think students particularly like this because, again, they like computer games. My only worry is sometimes you have to go around and say, okay, it's time to start the exercise, because I think they could play this for probably the whole class. So anyway, let me see. My time there is 9.92 seconds. That's how long I survived. Okay, so let's go back to the exercise. So let x be a random variable. Okay, it's a continuous random variable. It's going to measure the amount of time that you're able to survive the red block flight simulator before you get hit by a blue block or go out of bounds. People have been playing this game a lot, so let's imagine that people have been keeping statistics. I'm sure the person that owns the site has lots of very nice data on people coming and trying this experiment. But let's assume that x, the time to survive before getting hit by a blue block, is normally distributed with a mean of 15 seconds and a standard deviation of 3.75 seconds. So first, just sketch what that looks like. And for this first sketch, I'm just going to go ahead and do it by hand, and I'm going to show you how beautiful Minitab is at creating this and putting the tick marks in and giving a really nice visualization of this graph. So if I were to do it by hand, I have a normal curve. Let me go ahead and draw that in. It goes up to about, I should put a y-axis on here. This is f of x, the probability function. This goes up to a little bit past 0.1. The center of this is at 15. This is mu, right? Mu. The mean time that people survive on average. Again, we've looked at this. Let's say we have so much data that we're pretty certain that the true time to survive in this game is 15 seconds, and then with a standard deviation of 3.75. So one standard deviation, let's put that about right here and about right there. This then would go up to 18.75 seconds, and then 11.25 seconds, and that's one standard deviation away from the mean. About 66% of my data is in there. If I go 2 standard deviations, so that's about over, my drawing's not perfect, but let's say 2 standard deviations, that would take me to 22.5 seconds, and then on the lower bound, 7.5 seconds. And then let's say go ahead to 3 standard deviations. So 95% of my data is within 2 standard deviations. If I go out 3, it pretty much all my data is within 3. This is going to be 26.25 seconds, and this would be 3.75 seconds. Okay, so again, this is the distribution of x, which is flight times. And okay, so there's a pretty nice normal curve, and you could draw it by hand, but I want to show you how nicely this can be done in Minitab. And so over here, I did a screenshot of what it's going to look like when you go to Minitab, and I've written up, I thought, some nice directions. Oh, well, there it is right there. Go to graph probability distribution plot and view single. So let me pull up Minitab here. So there we go. Graph. Go down to probability distribution plot. Oh, I have the wrong one, sorry. Graph, probability distribution plot. View single, good. There's the normal. We had a mean of 15 seconds and a standard deviation of 3.75 seconds. And please draw that Minitab. And there we go. And that looks, I think, a lot cleaner than mine. And you can nicely see, like we said, this goes up a little bit past 0.10. And it's very easy for students to, copy and paste this into their document. So let me go ahead and do that. Let's go back to, well, actually I can't. I have, right now what I have up here is a PDF, so I'm not going to be able to cut it and paste it in. But I think you saw how beautiful that picture was. There it is, and there was my by hand drawing. Okay, so I did take a test flight, right? And I believe the time I survived, I might be off. I thought that was 9.92. If not, just humor me. Okay, 9.92 seconds. Okay. And the question I would ask then is, what proportion of flight times are longer than mine? If flight times are normally distributed with a mean of 15 seconds, right? And mine, my flight time was 9.92 seconds, so it's over. It probably would be nice to have this regular picture of there, but 9.92, we're going to be, about right in here, 9.92 seconds. I want to figure out what proportion of flight times, or what's the probability that somebody, does this test now and has a flight time that's greater than mine. So I want to find this area over here. And the way we're usually taught in class is just to find a z-score and then go to a standard normal table. So let's do that. So I want to find the probability of the random variable x, which is flight time, being bigger than 9.92 seconds. So what I'm going to do is take my random variable x, to standardize it or switch it to a z-score. I'm going to subtract off the mean, which is 15, and divide by the standard deviation, 3.75. So I want to figure out this is the probability of being bigger than 9.92 minus 15 divided by 3.75. And since I'm doing this on the fly, I have not calculated that, but this is going to be the probability that I get a z-score that's bigger than whatever this number is right here. So, I guess you're going to have to indulge me to pull up, I'm going to pull up Maple really fast just to do this calculation. So 9.92 minus 15 divided by 3.75. This will be my z-score, negative 1.35. So let's write that in there. What's the probability z is bigger than negative 1.35? Well, by symmetry, that's the same that the probability at z is less than 1.35. So let's go over there to our normal table. I think I have that up. Yep. And so let's go down 1.35. So I forgot to pull this up as an annotator, but there's 1.3. Let's go over. 1.35 is right there, my little hands on it. So that's 0.9115. 0.9115. So this probability is 0.9115 approximately. Okay, so that's the proportion of people that have flight times that are better than mine. So there's not going to be that many that are shorter than mine. That would be the complement of that. So 1 minus 0.9115. That's the proportion of people that had flight times less than mine. And this is slightly a trick question. What proportion of flight times are exactly the same as mine? There's no area under the curve at a point. And it's very, very unlikely if that truly is a random number and they stop at the right time. And if you could go out to many, many, many digits, it's unlikely anybody's going to have exactly the same time as mine. So, but in terms of thinking about area, there is no area under the curve at this point. So the proportion of flight times that are exactly mine in reality are 0. I mean, unless, again, we said we rounded to 2 decimal places, I'm sure somebody else has 9.92. But in reality, if I strung this out to the exact amount of time, there would be nobody else agreeing with me or having the same time. Okay, so let's check all this in Minitab. We found numbers, area to the right and left of 9.92, but Minitab is very beautiful at doing this, plus it shades the area for us. So let's go back in and let's go to probability distribution plots again. So let's get rid of this one. Okay, so graph. Probability distribution plots. This time I want to view a probability. 15.375 still in there. I'm giving it my time, my x value, which is 9.92. I want to find the area to the right, what proportion of people were had better scores than I did. And look at this. Isn't that that's very nice. So here's 9.92. This is the area to the right of it. And you see it calculated 0.9112. We use the table. Minitab is integrating, so its answer is going to be more exact than ours, but you can see how they line up very nicely. And notice again, I could cut and paste this graph and put it in my a Word document or a text document, but right now I have a PDF annotator, so I can't push it in. You can see easily then the amount of area to the left is 1 minus that. And again, there's no area right exactly at that point. So that's a very nice check. Let's go back to our document. So again, you can choose left or right. The time when I actually did, the last time I did this, I actually had 13.14 seconds that I put in as my X value. So I think, why I'm talking about this, if you are, showing students control charts or time series plots, students quickly get better at this. So let them play 10 times and you'll definitely see a graph that's increasing in time, flight times, the amount of time over the number of times they do the exercise. I'm not explaining this very well, but if you think of a time series chart, if this is their first time, second time, third time, fourth time trying the simulator, often they'll start at maybe, this is 5, 10, 15, 20 seconds. They'll start somewhere down around 5 seconds, and then maybe you'll get some around 10 seconds. And, they continue to improve. So I think it's nice to show, a process that's improving over time. And so what we say in quality is you don't have stability because it's still increasing over time. It hasn't settled down yet. And occasionally, too, I should say, you'll get that really bad time where, a friend or somebody was talking to you and you just kind of forget to pay attention and get a really low flight time. Okay, a few more questions. I'm going to form a Halo 3 team. That's something I could easily do at my school. But I want to interview applicants, only the really good ones. And the really good ones I'm going to consider are the ones that are in the top 1% of flight times, in the, this top little 1% right here. And remember that the mean was 15 and the standard deviation was 3.75. So I'm trying to find the students that have the top 1% scores. So again, I can go back and do this with the standard normal table, and that's how most of us are taught, or that we even teach our students. So let's go back and see what's that top 1%. So I'm going to go to the Z table again, and let's just say let's look at the bottom 1% by symmetry. We'll just flip over. Here we go. There we go right there. 2.32, 2.33. That's going to cut off about the top, bottom, or 1%. So I need 2.33, and the right tail will cut off the top 1%. So that's the Z-score. This is the Z-score that leaves 1% in the tail is 2.33. So if we convert that to flight times, that's 15 seconds plus 2.33 standard deviations to the right will give us the flight time that cuts off the top 1%. And if I multiply this out, I should get 23.74 seconds. And you can see I would not be on my own Halo team because my score was down at 9.92 seconds. So I think, again, we do a lot of this with normal tables, but Minitab, easily can show you what that cutoff value is. It's easy for you to change, 1%, 5% really quickly and look at different numbers. If you wanted to say, oh, I want to change and let in the top 5%, instead of keep converting to a table, you could do it easily in Minitab. So let me show you what I mean. Instead of putting in the X value, we're going to put in a probability and ask Minitab to find us what that cutoff is. So I'm going back here to Minitab. Let's clear this off and start again. So graph, probability distribution plot, view probability. We still have our normal in there, shaded area. This time I'm giving Minitab the probability, and I want 1%. I want to find that 1% cutoff in the right tail. So I choose right tail, okay. And it tells us 23.72. Of course, we use the table. It's being a little bit more exact. But again, there we find the cutoff value. And I think that, visually, it's very nice to see, that number there. 15 is the mean. 23.72 leaves 1% area in the tail. Students adapt really easily to be able to see the picture and then understand the probability. Again, a lot of it with the table is you get a z-score, and they totally lose sight of what you're doing. So let's see. So we looked at it a couple different ways. And to lead us into the next section, which will be the binomial distribution, I thought we'd do one more calculation. What's the probability that a randomly selected flight time will exceed 12.5 seconds? 12.5 seconds. So again, that's the left side of the mean. But let's see. So what's the probability of random? Yeah, so let's go ahead and find that. I can find that with a z, but why not just use Minitab right now? We've been doing so well with it. So let's get rid of this again. Graph, probability distribution plot, view probability. There's my mean, standard deviation, shaded area. I have an x value. It was 12.75. And I want to find, again, what proportion of people exceed that flight time. And we get about 7.257. And that's the number actually we would use going into the next section on binomials. So let's just 0.7275, right? Okay. So we'll carry this number in when we start talking about the binomial in our next session. Okay, so a big overview of this is we're looking at finding probabilities under the normal curve, and we did it with the z-scores by using the normal table, and then we went ahead and showed how we could do this with Minitab and with how much ease. And then I think my favorite part again is the picture. The students can visualize what it means to be area under the curve and how that relates to probability, and to easily switch. Change up different numbers, try different probabilities, try different x values, and see a variety of calculations without having to go back to the normal table over and over again. So we'll add to this later, but for now, we'll see you soon and make another video. Thanks.